This is sound pressure, and this is where everything starts because it's really the building block for everything else we're going to talk about today. So real fundamentally, what is sound? Well, sound that we perceive with our ears is really just pressure fluctuations, most typically through the air, that are caused by a vibrating surface. Could be a speaker in your home, could be my vocal cords right now, or hopefully your speakers, however you're listening to me. If you were in this room right now, you would hear my vocal cords vibrating. But those vibrations cause the air next to the sound source to also vibrate. And then as you see in this illustration at the top with the tuning fork, the air molecules bump into each other, and that momentum is sort of passed on to the molecules next to it, and it transmits away as a pressure wave. And so we have these particles getting closer together, which causes the pressure to increase, and then we have the particles spreading apart, which causes the pressure to locally decrease. And so we have this oscillation, and that makes a sine wave a very useful analytical tool to describe and analyze sound waves. And so if you look at this sine wave down here at the bottom, you see the areas of pressure increasing where the particles are coming together, and then you see the valley of the sine wave where the particles are actually stretched apart. And so we use the sine wave to sort of analytically describe sound waves and analyze them from a frequency perspective. So if we talk about this sine wave, there are some characteristics of the sine wave that are going to be very important. Not only the amplitude of the sine wave, obviously very important, but also this thing called the period. And the period is in the time domain, and it's the amount of time it takes the sine wave to go through one cycle. Okay, so that's how many seconds. The inverse of that period is the frequency. So many seconds per cycle, we invert that, and it's how many cycles we get in 1 second. This is what we call the frequency. And most often we're working with frequency when we're talking about sound, just because that's usually amplitude and frequency are what we're talking about. We don't often work with period. And if we took the human hearing range in terms of frequency and we gave it some nice round numbers, we would say that range is roughly between 20 hertz on the low end and 20,000 hertz or 20 kilohertz on the high end. Almost no one can hear outside this range. Below it, the frequencies are so low that we really perceive them maybe as, pressure fluctuations in our chest or something like that. And then above 20 kilohertz is called ultrasound. This is in the region of dog whistles and things that are too high for us to hear. Okay, so that's the period and frequency of the sine wave. We also have a physical property of the sine wave, which is its wavelength. This is measured in meters, and it's the physical size of this sine wave. Again, for it to go through one cycle, we measure that in meters or in unit of distance. Okay, and that is related to the speed of sound. Certainly the lambda is the wavelength, and certainly the speed of sound will affect it, as well as the frequency. So low frequencies have very long wavelengths. High frequencies have very short wavelengths. Okay, that's what helps us perceive the difference in frequency or pitch. Just to give you an idea, if you look at a 34 hertz sine wave, that wavelength is 10 meters roughly. So like 30 feet long. When you're hearing a 34 hertz sine wave, you're experiencing a wave that's 10 meters in size. So it's very, very big. And so this is going to play an important part later in the afternoon when we talk about diffraction and absorption and trying to control frequencies. We'll see the wavelength plays a very important part.
That thing is huge, huh? And it gets much smaller as you go higher in frequency. It's kind of like a stereo system, where you get woofers and tweeters. The woofer, I guess, you can put anywhere in the room, and it fills the room with bass.
Yep, exactly.
Tweeter is very directional. I know I had to position those very carefully towards the couch.
Yeah, you focus those kind of, right? Yeah, and
that's because
typically
of the wavelength, huh?
And the subwoofers are typically larger because you need a larger surface to vibrate to adequately create that low frequency with the large wavelength. That's exactly right. Great point. So that's wavelength. And we talked about this a little bit, but sound is measured as pressure fluctuations, but it's important to understand that we're talking about fluctuations sort of above and below some mean pressure that we call atmospheric pressure, right? And the pressure fluctuations that we're talking about in sound are typically very, very small, especially compared with atmospheric pressure. Often we're dealing with pressure fluctuations on the order of 20 micropascals, or 0.00002. I've got 4 there, right? 0.00002 pascals, all the way up to 20 pascals. That's like the human dynamic range in terms of amplitude. Compare that with the atmospheric pressure, which is 100 kilopascals. And so we're talking about very, very small fluctuations on top of a very large static pressure, okay? But it's important to understand that where you see these dips in the sine wave where it's going below zero, we call zero atmospheric pressure. It's not really negative pressure like a vacuum or something. It's just a smaller pressure than atmospheric, okay? So it's important to understand that when we always show sine waves sort of around zero, but it's not really negative pressure. It's also important to understand how our brain processes pressure fluctuations as opposed to maybe how a microphone might. A microphone, if you look at this red time history down here in the lower right part of the screen, this is how a microphone measures and experiences this sound pressure fluctuations as instantaneous fluctuations of pressure. Our brain does not hear this instantaneous pressure fluctuation. Our brain sort of groups and lumps chunks of time together, and we report an amplitude at a certain chunk of time. So we sort of use our brain uses an integrator function, if you will, to grab a chunk, say, let me think of this as a chunk of time and frequency, and we experience that chunk as one whole thing. So for human beings, we often will use what we call the RMS, or the root mean squared sound pressure level. It's a mathematical way of summing up the pressure over this chunk of time. Okay, and so we'll often talk about the RMS amplitude as opposed to the instantaneous amplitude or the peak amplitude. Okay. If we look at the audible range of sounds for the human being, from something so quiet we can barely hear it all the way up to something that's so loud that it's painful for us to listen to, and we looked at those measurements in terms of pressure, the unit of pressure that we'd measure with a microphone, we will see that something that's barely audible, again, we have this 0.000063 pascals. Someone whispering in your ear, very, very small pressure fluctuations. And then if we go up a unit of description, so from barely audible to something we'd call quiet, we see that it's 0.00063, so we've dropped a 0. Go up to something we'd say moderately noisy, 0.0063, drop another 0. Something we'd go from moderate to noisy, drop another 0, it's 0.063. Something very loud like a heavy truck is 63 hundredths of a pascal, or 6/10 of a pascal, okay? And then go all the way up to something that's painful like a jet taking off, and we'd measure that about 20 pascals. So if we look at this range, we see it's an incredibly big range, right? Not very often where you're making measurements that you're writing down numbers like 20 and writing down numbers like 0.000063 in the same measurement, okay? Dynamic range of human hearing is very, very large, and this aspect of our hearing makes Pascal, the unit of pressure, kind of inconvenient for us to use. These numbers are so different that it's just hard for us, it's sort of awkward for us to use these.
Well, you used to work at a noise and vibration department, Scott. Didn't you guys say oh, that one's much quieter, it's 0.0045 pascals, and no, this one's 0.0037, and was there a lot of 0.00 discussions?
There was initially, but they found it was costing so much time for us to talk that way that they decided to switch to something more efficient. So while I was there, they switched over from talking in 0.0000s to using the decibel. It saved us a lot of time, put our company back into the black. It was great.
0.00s or not?
We were 0.00s, but there every once in a while someone would come over from Europe and they'd be
a notter.
0.0, yeah.
Aught?
The aughts. Yeah,
okay.
Knots, aughts.
This scale looks a little more reasonable here with these
it sure
decibels.
does, and that's the whole point, right? And so we're using this thing called the decibel, and so even lay people are often aware of this unit of dB or decibels for sound pressure. We're going to explain how it works so that you have a better understanding. But you see what effectively the decibels do is it squashes this dynamic range, and it makes the very low end or very smallest number and the very highest number a lot closer together. 10 and 120, those are both whole numbers, integers, so we're already a lot closer together, so it makes it much more convenient. And you see, before we were just dropping off a 0, so there is this factor of 10 built in, this sort of logarithmic aspect to our hearing ability. Those equate to some very nice round numbers in decibels. And so the decibel is going to be very convenient for us to use for sound pressure levels for a human being. So how does this decibel work? How do we convert from pressure in pascals to decibels? We use this equation. And it's really just a logarithmic ratio of two numbers. That's all a decibel is. And it isn't specific to acoustics or sound pressure. You can take any numbers and theoretically convert it into decibels. It's really just a logarithmic ratio. We use it for pressure because of those aforementioned aspects of human hearing. Okay, so we take pressure from our measurement microphone, we divide that by what we call our reference pressure, and we all need to agree what this reference pressure is. And then we take that ratio, take the log of that, multiply by 20. That's your sound pressure level in decibels. Okay.
Are you moving your laser pointer?
No, I'm not. I was waving my hands. I was gesticulating, but you make a great point. I should be using my laser pointer, particularly for you who can't see me or my video feed here. But you're right. We're making a measured pressure up here. We divide that by a reference pressure, take the log of that ratio, multiply by 20, and that's our decibel. Now you notice in this equation, we're always talking about this pressure that we're measuring as an RMS quantity, so it's important to understand it's not a peak or a peak-to-peak value, it's an RMS. And the reference pressure we'll use in all of acoustics is 20 micropascals, or 20 times 10 to the negative 6 pascals. Okay, and we'll talk about where that reference pressure comes from, but this is how you convert pressure into decibels. Okay?
Looks pretty straightforward.
Yeah. So if we look at this conversion for decibels, we'll use decibels, and we call it sort of the original sound quality metric. Sound quality metrics are trying to make sound and the qualities of sound, like amplitude or frequency, more convenient for us to use for human beings. Decibel takes that awkward Pascal scale for human hearing and converts it to something much more convenient, and it sort of matches our perception. So that's why we use decibels. So if we look at this conversion and we take that reference pressure and we plug it into that equation, so now we're measuring 20 micropascals, we divide that by our reference, which happens to also be 20 micropascals. That ratio becomes 1. And Pete, do you remember the logarithm of 1? What is
that's
that?
A big naught, 0.
That's right, it's always 0. So when you register 0 dB on your sound pressure level meter, that means you are measuring your reference. Okay. Now if we jump up to much bigger number, 1 Pascal, nice easy round number, convert 1 Pascal into decibels using that same formula, we'll calculate 94 dB. Okay, this is often used for microphone calibration. It's a nice round number, 94 dB equals 1 Pascal, and so it's just a nice convenient unit. Now, something interesting is I'm going to show you here where I take 1 Pascal and I double that, and I go from 1 Pascal to 2 Pascals. I've doubled the pressure. What happens to my decibel value, Pete?
Yeah, 94 to
Yes.
100 is a 6 dB
6
increase.
dB. Yep, so we went from 1 to 2, so an increase of 1 Pascal is 6 dB. But now what? Let me show you something weird. I'm going to double it again. I'm going to go from 2 all the way up to 4. So now my increase is twice as much as it was last time. Now how much does it go up?
100 to 106, 6 dB. So
6 dB.
Again, 6 dB.
Yes, so this is the price we have to pay for the nice convenient aspects of using decibels for human hearing. We have this awkwardness where you have to sort of take the good, take the bad, you take them both, and there you have the facts of the decibel. Where 6 dB is always a doubling in your root measurement. So no matter what, if I'm going from 2 Pascals to 4 Pascals or 100 Pascals to 200 Pascals, that increase will always just be 6 dB. Okay.
That's
so it's
crazy.
a little bit awkward. Yes,
It's
it's
like,
very
boss,
awkward, but
I've reduced the sound of the product by 50%. The sound pressure's gone down, and it's went from 66 dB to 60.
yes. And if he doesn't understand this aspect of decibels, you might be in some big trouble.
Yeah.
You'll find yourself talking in OOOs and nots.
Yeah.
Pretty
or
soon.
put on a special list and can end up working for Siemens or something.
We all end up here sometime, don't we?
Yeah.
So I just like to show this. 6 dB is really just a factor of 2. If you drop 6 dB, like Pete just mentioned in his example with his boss, he went down 6 dB, cut the sound pressure in half. 20 dB relates to a ratio of 10. 40 dB is a factor of 100. Okay, so it's making these really big changes in the linear unit of pressure don't always equate to big changes in the decibel. And we're using that to our advantage with the big dynamic range of hearing, but it kind of comes back to be a little bit awkward where you have to keep this doubling as a 6 dB change. It's just a little bit hard to keep track of, but we'll address that when we get to some more advanced topics later. Okay? But let's talk about summing these values now. Okay, so this is an important thing. I've got multiple sources on my machine or whatever product I work on, and I need to reduce the sound level. Let's learn about how these things sum together. Let's say I've got 2 machines, they're running in my office simultaneously, and each of them makes 2 pascals of sound pressure or 100 dB. What am I going to calculate for an overall level with both machines running?
Probably like 200 dB. It's going to be pretty loud.
Well, we always work in the root unit, so we always sum the pascals first. So, we talked about 2 pascals plus 2 pascals is 4 pascals, right? If we just did a straight linear summation. So we might say a doubling of pascals should give us 6 dB, right?
Yeah.
Well, this is going to highlight an important aspect of summing sources in noise is that we can't just take a straight sum. We have to do this RMS sum. Okay, this root mean squared. So we have to take 2 squared plus 2 squared. So that's 4 plus 4, that's 8, and take the square root of that. And so the square root of 8 is 2.82. That's actually how many pascals we get when we sum them together.
Yeah, that makes sense.
And we're going to talk about why this phenomenon happens, but 100 dB plus 100 dB is actually 103 dB.
Wow.
Okay? Yeah.
I was a little bit off with 200 dB.
A little bit, but we've come to expect that, and it's just part of the magic of who you are, Pete.
Yeah, magic. I don't know if that's the right word.
So 3 dB increase in adding together our 2 sound sources. So why does this happen? Well, we have this thing called coherent and incoherent sound sources. It makes a big difference. And coherence is just a fixed phase relationship. In my previous example, I had 2 random sound sources, so they're just playing noise in a random fashion. So there's can be no relationship between these 2 sources, and so they're incoherent. And so what's going to happen is sometimes these things are going to be acting together and they're going to sum together, and sometimes they're going to be acting opposite and they're going to cancel. Okay, and so if we look at these 2 sine waves with a real simple example, each of the
these
sine
are
waves
like the 2 sources and the pressure fluctuations coming out of them.
Yes, so we're measuring source number 1 in the red, and you see it's about 2 pascals of a sine wave of a pressure oscillating back and forth. The second sound source, also 2 pascals, it's shown in green here. But you notice that they're at slightly different frequencies, and so sometimes they are adding together. Like right here, they're both pointing down, so they're going to sort of constructively interfere with each other, and we're going to get 2 plus 2, and you see the magnitude is now like close to 4 down here. So they're in phase, and the signals add together. But a short while later, a couple cycles later, now they're completely out of phase. The green is going up, red's coming down. Those cancel out, and we essentially get 0.
Wow.
Okay, and so we go from 4 to 0, and we're going to kind of bounce back and forth between those 2 numbers, and that's why we can't just sum 2 pascals plus 2 pascals, because sometimes it's 0 and sometimes it's 4, and so that's why we use the RMS sum when we're summing sound sources.
So we won't be quite as tall as the highest blue peak, and we won't be 0 either. The RMS is somewhere in between.
Yep. Yep, exactly. So we got to keep this in mind when we're summing sound sources, okay? So now let's move on to a little bit more complicated example where now I have 3 sound sources and they're all at different levels, okay? So sound source number 1 is 10 pascals or 113 dB. Sound source number 2, 2 pascals at 100 dB. Sound source number 3, also 2 pascals, 100 dB. What do you think I'm going to get if I sum source 1 plus 2 plus 3? I've got them all running at the same time. Well,
luckily the answer is there on the slide.
Right, it is. And it's 114.3 dB. Again, we're going to do this RMS sum. So 10 plus 2 plus 2, that gives us 10.3. Convert that to decibels, 114.3.
That's 10 squared plus 2 squared plus 2 squared, all square rooted, 10.3.
Correct. Yep, exactly.
What
do you notice about this sum, 114.3?
That 114.3 is very close to source 1.
That's right. When I'm working with Pete, I like to put the answers in big boxes right from the start so he doesn't get too lost.
I appreciate that. Always.
But he got it right this time. Well, yeah. I'm here for you, man.
Well, you know, I do have trouble reading what's in front of me.
Well, that's because you're so far ahead of everybody else that you often miss the most obvious. But yeah, Pete's right. Sum is almost identical to the largest source. Source number 1 is 113. We add 2 100 dB sources on top of that 113, and we really only get to 114.3. Okay. So 113 plus 100 plus 100 is 114.3. Okay. Again, we've got to do this RMS sum, but we see that largest source dominates. Okay. So we do a bunch of work. Pete and I work all weekend, and we work on source number 1, and we drop source number 1 from 113 dB down to 100 dB. Okay, so now we've brought it down to the same level as our other 2 sound sources. Now what do we get? Well, we turn them all on. We measure, again, an RMS sum, 3.46 pascals, and we convert that to dB, it's 104.7. Okay, so by taking 13 dB out of source number 1, we drop our overall level with all 3 running almost 10 dB. So that was a huge improvement. So we're on a good special list now, I think, after working all weekend.
Yeah.
But we go to our boss and he says, well, the target's 100 dB. So great work, but you're not there yet. So Pete and I, it's Friday afternoon. We want to go home. And so we do something drastic and we just say, all right, let's just chop off one of these machines. They paid us for 3, but we're only going to deliver 2. And so we cut out a whole 100 decibel source from our noise problem. What's our overall level now? Well, we know this, 2 pascals plus 2 pascals, RMS of 2.82 pascals, which gives us 103.
That ain't much far off compared to where we were
We've thrown
before.
away 100 decibels of noise, and we've only gone down 1.7 decibels in overall level.
We removed a third of the noise, and we've hardly knocked down the dB. It's crazy.
Exactly. But now it's like Friday afternoon. We're really desperate. We're like, let's just rip out source number 2 as well. So they paid for 3. We're only going to give them 1. Now we're finally at 100 dB, but we've also taken away 2/3 of what they paid us for. So we're going to be in big trouble. But it highlights an important aspect of working with sound when you have multiple sound sources. Instead of going and attacking one sound source, if you have all equal source strengths, or you have 3 sources, multiple sources that all have the roughly equal strength in terms of level, you're better off addressing each of them a little bit to bring down the overall level rather than attacking one and taking it totally out, because it's not going to help.
Like if we had lowered each 100 dB to 90 dB, so we had 3 90 dB sources,
yes,
we would have hit our target. And yeah, we're only would have removed 30 dB overall. Here we removed 200 out of 300, barely got there. But if I had just removed a little bit on each one. Wow, these little things off to the side there are useful. Better strategy. Address each source a little bit. Yeah.
Well, like I said, I'm here for you, Pete.
Yeah.
Okay, so that's some of the funny math, as we call it, working with decibels and multiple sound sources. So with all this complication, why do we use these decibels? Well, we hear sort of logarithmically, and so using a logarithmic unit makes it much more convenient for us. Much more convenient than the linear unit of pascals, okay? So ultimately, it's about convenience and making it easy and reducing errors when we're working with sound. Got a quick demo Pete's going to show us. We'll see how these decibels and A-weighting work in practice.
Yeah, I can do a little demonstration here of what's in the room, Scott. So here I'm actually measuring the sound pressure in the room through this thing called a Scatus XS. It's hooked up to my computer. And it's showing the Pascal level here on the y-axis, frequency on the x-axis. And this Scatus XS is hooked up to this binaural headset. So this headset actually has a microphone in each ear, and it's being fed directly into the XS. I'm showing just one of the microphones. If I whistle, we'll see the frequency of my whistle there. So that's the Pascal value. I can put a cursor on here. And what do we think the frequency of my whistle was? Looks about 1,235 hertz, 0.09 pascals. And so you might be wondering, what is that in decibels? And it's pretty easy here in the SimCenter Test Lab software. I can go right-click on the y-axis, Format, dB, and it'll plug that Pascal value into the equation you showed earlier, and it converts it, and we get it, it shows it as 72.67 pascals. Pretty cool, huh, Scott?
Very cool.
And it did that at every single frequency. So not only did I get a Pascal value here at 1200, I got Pascal values across the whole frequency range. So what is the overall sound level here? Is it 72?
No, it'll be 72 plus an RMS sum with all these other values, right?
Right. So it's not the highest value that gives you your dB value. So if you read in a magazine or something like this car is 80 dB or something, what they're actually doing is they're doing a summation across the entire frequency range, and they calculate a RMS sum of all those frequencies. So you can see that that is a little bit higher because, like you said, yep, Scott, it includes everything else in here. And in fact, if I start moving this cursor, now I'm summing over a smaller region, is it changing that value very much?
Not at all.
And that's because the largest peak is in there, just like we had earlier when we had the one source at 113. And so if I come down here and eventually get past that source, then there's a big difference there, huh? You can see that the levels went way down when it wasn't included, and they go way up and don't hardly change when the biggest peak is included.